Hey guys, today we're going to be talking about transformations of functions. We're going to start with quadratics and then go to more general rules that work for all functions. And so if you have the function f of x equals x squared, again the most basic quadratic, what is really the effect of doing things like adding 2 on the end, and how is that different from adding 2 inside of the parentheses? So let's start by thinking about this graph of x squared. You might be familiar with it, but to review, let's say we make a table to really think about the shape. If we plot from -3 all the way to +3, okay, when you square a -3, it becomes a +9, because negative times negative is a positive. If you square -2, you get 4. Square -1, you get 1. Squaring 0 gives you 0. Squaring 1 gives you 1. Squaring 2 gives you 4. Squaring 3 gives you 9. So that's why when we graph it, it looks kind of like this. So if I go over 1, 2, 3, 1, 2, 3, I go 1, 2, 3, 4, 5, 6, 7, 8, 9. If I'm looking at the graph of this one, it starts here, comes down to 4, and then comes down to 1, then to 0. So this is why it's a parabola shape. It kind of curves up. It's mainly because of this principle on how if you square a negative, it's positive. Square a positive, it's also positive, right? So that's a general graph of x squared. Now, let's analyze what happens specifically like in a table if now we're just adding 2 on the end here, okay? And if you could think about it, because we already have this table over here, it's going to be easier to calculate, because x squared plus 2, we already know x squared. If you, let's say, have x equals -3, if you square it, you get 9, then you just add 2, it's 11, right? And so then from this one, we go from there to there simply by adding 2, and notice the same thing is going to happen every time, because you have your value of x squared is 4, you're going to add 2, and you get 6, right? So we could essentially fill out this table simply by taking the table from the blue one and adding 2. Because, again, -1 squared is 1. Add 2, you get 3. 0 plus 2 gives you 2, okay? So what I'm doing here, now, again, same thing, it's symmetric. And so if I think about what that really does to the graph, if I plot this over here on the same axis, okay, all these points are just 2 points higher. So I go 1, 2, 1, 2, 1, 2. Notice how this one is just 2 points higher, and so this one is like this, okay? So this graph here is g of x, and this graph here on the black, maybe I should have made it blue, this one's f of x, it's the original, right? And so adding 2 on the end moves it up. Now, and similarly, if I were to just write another function, let me use a different color, and let's say j of x equals x squared minus 2. I don't really have to make a new table. I could kind of think theologically, it's going to do the same thing, right? But the other direction. That would just basically move you down 2 spaces, right? And that would be lower, okay? So, and this is true not just for x squared. Again, we're kind of build up to see the general rules. No matter what the function is, if you're just adding 2 or subtracting 2, or adding or subtracting any number, when you're adding at the end, it's like that, because of order of operations that doesn't last, that's going to shift the graph up or down, okay? Now, let's think about what happens for this last case. What about if it's inside of the parentheses, okay? So if I think about this table, I'm going to have to break this down a little bit more and think, okay, if x is -3, let me maybe off here show how to calculate. So I'd have -3 plus 2 squared. Well, -3 plus 2 is -1. Okay, square it, you just get 1. So -2 plus 2 gives me 0. 0 squared is just 0. And then -1 plus 2 is 1. And then notice it's going to keep going up 1 on the inside. So if I have 0, 0 plus 2, 2 squared is 4. And so notice then 1 plus 2 is 3, 3 squared is 9. And so we see the same numbers basically as we did over in this table. But now notice how it's kind of shifted up, right? 2 plus 2 is 4. 4 squared is 16. So what that means then, when we're graphing it, notice this key point right here is the 0 where the vertex is. Notice now I'm going to basically count over to -2 right here. And the graph is essentially the same shape, but now it moved over, right? Now, this is the one that's confusing to the most people, I think, because, and again, I'm just going to draw it up here again so you can see it where the graph is not cluttered. Notice there was a plus here, and it moved to a -2. That'll throw people off. It's like, wait, why does adding on the inside move you left? Usually plus means go positive, right? But it's because you see it right here, because what's needed to get that vertex value being 0 is you did a -2. So when it's inside the parentheses, it does opposite. And similarly, if let's say I was going to do another function, let's say k of x was equal to x minus 2 squared. Well, if we think about it, what value is going to make this 0? Well, if you had a positive 2, 2 minus 2 squared would be 0. So by subtracting 2 on the inside, I would go over here to the positive, and hopefully we can kind of understand it would be the same general mode, that if you move that way to the right, again, I'm going to graph this on this graph here, right? Then this would be k of x equals x minus 2 squared. Okay? So because you're minusing on the inside, it shifts everything to the right. So the key rules here, adding a number on the outside is going to move you up or down, and adding a number on the inside is going to kind of move you opposite. Adding moves you to the left in the negative direction, subtracting moves you right in the positive direction. Now, everything on this page right here is what we call translation. So translation is an important type of transformation. Transformation is anything that's kind of moving or changing the shape, but a translation is, notice the quadratic graph is about the same shape, you're just sliding it. Imagine the graph, it's kind of like you slide it up, down, left, or right. So these ones all here, these are all translation examples. So next, let's look into the other type of transformation, which is dilation. And so when I talk about dilation, there's a couple ways you could talk about it. You could talk about stretch or compress. And when I talk about dilation, I'm also going to talk about and reflection. So reflection is like reflecting something over the axis, right? These are terms from geometry also. So let's say I'm going to write it in black this time. I have my original function f of x equals x squared. Okay. Now my new function, I'm just going to call it a of x this time, and I'm going to say 2 times x squared. So let's consider these tables. Again, I'm going to rewrite this one where you have x and you have f of x. I'm going to go and just fill it out because we already did this before. Again, you calculate x squared, and then order of operations you multiply by 2. So I can think about taking this one, and then now I'm timesing 2 instead of adding 2. So that would be 18. That would be 8. Now, 2 and then 0, and then 2, 8, and 18. Because I take this number and I multiply by 2, right? So if we graph this on the same set of axes now, let me do it over here on the right. Remember, the x squared graph looks kind of like this. Okay, f of x equals x squared. So what's happening here is that now these numbers are twice as big. We notice that the vertex is the same. Notice the vertex didn't move, so we didn't translate it, right? So the vertex is the same, but now this point, -3, is at 18. So let me go ahead and put my points here. Let's say I did 1, 2, 3. So this point, first point was 3, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I go 10, 11, 12, 13, 14, 15, 16, 17, 18. So now this one is higher, right? It's all the way up here. And this point was about at 4, right? But then you go up to 8, right? And instead of being down here near 1, 2. So you see what this did is it stretched it, right? It's a stretch. Now, to consider what's the other type of compression, dilation, or reflection? What if we had b of x? Let's call it 1/2 x squared, okay? So if we consider this one, now, well, what's half of 9? It's 4.5. Half of 4 is 2. Half of 1 is just a half. Notice the 0 is still 0. And then we know it's symmetrical, so we see the same numbers again. So what that does is now these numbers are lower. It's like down here, 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 and here. So basically the rule is if you have a number in front of x squared, being multiplied by x squared, and in general, again, this is going to be true for any function. It doesn't matter if it's x squared, if it just could be any function. Hopefully you notice that whatever this is, you're going to multiply that by 2, which is going to stretch it up. Whatever the original function is, you're going to multiply by a half, which is going to compress it down. Okay? And then the last one I want to cover is thinking about, well, what if you put a negative in front, right? So I'm going to call this c of x. I'm going to do it over here and call it negative x squared. And see, this one is going to be very similar because all I'm doing to this table is you just add a negative in front, right? Negative 9, negative 4, negative 1, 0, 1, and then it turns negative again because you squared it and then you add the negative, right? So there's 3 and negative 9. So what that does, if I'm over here on the negative, like negative 9, negative 4, it's going to be just like the black graph. Again, I don't have actually plots that I don't have the grid to actually plot the points right now, but you see how it's reflected over, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. It'd be like this, right? But hopefully you see these are going to be down in the negative zone. So if you put a negative in front, that reflects it. If you have a number in front, that's either going to stretch or compress. Numbers greater than 1 are going to stretch it up. Numbers that are fractions are going to compress it. So here's a nice summary table. Rules for the description of graphs of transformations in the form a f of x plus h plus k. Now, you might be wondering, what in the heck is this? So this is what if you did all the transformations at once, okay? Now, before we dive into the rules, let's actually look at one example of that for the quadratic. As if you had a f of x plus h plus k, right? So if our original function is f of x equals x squared, so if I want to multiply something in front, add something in the middle, and add something on the end, let's do an example of that. Let's say I have this function g of x that is negative 3 f of x minus 4 plus 5. Okay? For example, so in this case, g of x would be negative 3 times x minus 4 squared plus 5. Okay? So notice how this is in general. You could apply this to any function, right? You could add a number in front, do something on the inside. This is how it applies to this specific example where f of x is x squared. Okay? I put a coordinate axis here to make it a little bit easier to graph more precisely for this one. So x squared, starts 0, 0, then goes to 1, then when 2 squared is 4, and then 3 squared is 9, 6, 7, 8, 9, right there. So we can say with confidence, this is the graph of x squared, the original. So how we're going to graph g of x is we're going to consider all the transformations. So we can start at the front if you want. So remember that negative 3 is a stretch because it's a 3. You're multiplying by 3, but it's also a reflection. So first of all, like if you look at the very first thing, the negative is a reflection over the x-axis. So I'm going to maybe draw my steps in dotted lines. So it's going to reflect this way, but then also imagine taking every point and multiplying by negative 3. It also stretches it down 3. So this point now goes to negative 3. This point, which was positive 4, is going to go to negative 12. So it's pretty skinny. It's kind of off the page now, but it's going to look like, I'll make sure to go through this point, negative 3, and it stretches down, right? So that's what the negative 3 did. Now, the minus 4, remember, if you have a subtraction on the inside, that moves you to the right. So this moves you to the right, and actually, instead of a solid line, I should do like a dotted line here. This is just like my first step. I'm just kind of showing my thinking here. This is not the final. So now, this also has to move to the right by 4. So then this is going to come over here. But it's going to move, every point is going to move to the right 4, but also up 5. So let me just count 1, 2, 3, 4, and then up 1, 2, 3, 4, 5. We're right here, right? So I'm going to do that with each of these points, right? I'm going to go 1, 2, 3, 4, and up 1, 2, 3, 4, 5 right here. Now I could also kind of count down. Notice that when you went over, you went down 3. And then also this, I said it went off the page, but I said overall from the top, the maximum is going to go down 12. So maybe I can do that now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the next point is right here. And again, the reason to kind of elaborate on what I just did, you know that this point, which was 9, you know that, sorry, this point wasn't 9, it was 4, right? 4 was right here. If you take 4 times the -3, you get -12. So that means that from that top point that far to your third point over is down 12. So, but you see the overall idea is on what this did. So the beginning, and you could do this in any order. You could have moved it, translate it first, and then show the stretch down. I find it easier to do the compression first, or the compression or the stretch, because you just multiply all the point values by that number -3. So now if I connect this, this is my new graph. Boom. That is g of x is -3 parentheses x minus 4 squared plus 5. Okay? So what I'm going to get to next is, let's say we had some other function, f of x. It doesn't matter what f of x is, the rules are going to be the same. Is that this is going to reflect it, and then also stretch by a factor of 3. This is going to move 4 to the right, and this is going to move up 5. Now, I do want to add a note about this form, especially that had the plus h. Now, what you'll normally see, there's a form of the quadratic equation called vertex form, and they write it like this. The vertex form of a quadratic is ax minus h squared plus k. Because if you do that, remember that when we subtracted 4, it actually moves you positive. So in order to be a kind of standard, if you wrote it like this, then h comma k always is your vertex. So like in this case, the vertex is the point 4, 5 because you have -4. So what a lot of times people do when you see the translations is the negative is worked into the equation to show that whatever h is, it's like you're doing the opposite. I went ahead and wrote plus here just for your understanding as far as like building these concepts, that if you add something in, realize it does the opposite. But notice that just like the vertex form of the quadratic, you will a lot of times see the negative in the equation to show, hey, x minus h means that in this equation, you see x minus 4, h is a positive 4. So let's go back here now. This is the rules for any function in general. So remember that step 1, you can stretch or compress the statement. So if a is greater than 1 or less than -1, right? You're going to stretch by a. You can just say, hey, it stretches by a. So this is talking about how you're going to describe it, right? So for example, doesn't matter what f of x is. If you had 3f of x plus 4 plus 1, you'd say vertical stretch by 3. And also it reflects over the axis. So rule 2, reflection over the axis. Again, if a is negative, reflect over the axis. If a is positive, you don't need to say anything about that. Okay? Now the effect of h. If h is positive, again in this form, meaning if you're adding a number inside the parenthesis, say move h spaces to the left. So here we plus 4, we move 4 spaces to the left. If you had said -4, you'd move 4 spaces to the right. Now the effect of k, that number on the end, if it's positive, you move it up. Negative, you move that many spaces down. Right? So next example, you say with a 1/2 in front, you say vertical compression by 1/2. -3 on the inside says move 3 spaces right. -2 on the end means move 2 spaces down. Now, with these rules, there is kind of a shortcut for moving the points if you want to. Now, again, this one's not a quadratic. Looks like a cubic or something, right? But the overall rule then, at any point, you'd pick key points, like let's say this point, that point, right? And then you would basically take your x value, subtract it by h, your y value, you multiply by the y, and then add the k. So, for example, if this was f of x, and I want to do -3 f of x plus 4 plus 1, so notice, I note what the key points are right here. So I got this key point right here. This key point is -4, 1. And let me just note 2 of the key points. And this is 0, negative 3, right? See, that's where we're getting this and this, okay? So negative 4, 1. Now look at this. It goes negative 4 minus 4, which becomes negative 8. And then if I'm looking at the y's, I'll do the y's in this. So negative 3, which is the a value, times 1 plus 1 gives me negative 2, okay? Now, the other way you could do it, you could also just think about the transformation rules, and you could think about, okay, I'm going to stretch it, but again, stretching is reflecting, moving down here, and then I look at the transformations. I'm going to move left 4, 1, 2, 3, 4, and then I move up 1. So notice it's really the same thing. It just shows mathematically how it happens, right? 0 minus 4 is negative 4. Then negative 3 times negative 3. Again, that's taking this point, and you're going to stretch it by negative 3. So you go down to, actually it flips up to positive 9. And then you actually move up 1 more, and I move 4 to the left. So it ends up right here. Okay, so these are the two new points. Now, the other thing you got to just kind of think about, I realized that my entire graph flips. So if it started off going like this and this, now it's going to come down, hit this point, come back up, hit that point, and then come back. Now the other way to do it, you could look at like x-intercepts and such, but that's a great example. Notice how this graph I drew right here in red is this graph we got that we figured out from there. So I hope that helps with how to do transformations and understanding the transformation rules.